Hi, everyone. As we agreed in class regarding the video lectures, I just want to proceed with what we agreed on so that you can have this, go through it for the class that we lost. That's on this week's Monday as a result of the Independence Day. So we ended on the preliminary or the basis. So currently we just want to move on to the actual studies. This was where we ended the other time. So the actual studies, we are looking at circuit laws. And for the circuit laws, there are some important aspects that will be looked at. We would look at voltage, potential difference, and EMF. I've already spoken about that to some degree. Conductance, resistance, conductivity, and resistivity. Electrical energy and power. Resistors connected in series and in parallel. We'll look at how to find the total resistance. Then we'll look at the voltage divider rule and the current divider rule as well. Before we'll go to Ohm's law, Kirchhoff's laws, and some network solutions. Let's bear in mind, around this time, somewhere within the lecture, we'll be considering transformation of voltage sources to current sources and vice versa along the way. So as I taught you earlier on, that's just a repetition. Another word for voltage is potential difference. Potential difference or EMF. Okay. So that's how we do measurement of voltages and current in a circuit. For a voltage measurement, we can clearly see that there's a simple circuit that I have here. I have a voltage source, there's a resistor, and there's a series connection because I have the current moving in only one path. There's no branch or junction for the current to be divided or any current to be left behind. All right. For us to measure the voltage, normally we connect the voltmeter across the element that we want to measure the voltage across. So if I need to measure the voltage across this very particular resistor I have here, the voltmeter should have its terminals connected across R. When it comes to current, current is normally a case where you have to break the circuit and connect the ammeter in series with the network. In series with the network. So let's kindly take note of that. These are worked examples. It says that we should determine the conductance. We've already met the formula in our previous lecture, the pre-lessons before the chapter 1. To determine the conductance of the following resistors. So we have 5 ohm, we have 100 kilo ohm, and we have 50 milli ohm. And as you remember, conductance is just the inverse of a resistor. So that means that to calculate for the conductance whose unit is in Siemens, we just need to take the inverse of each of these values. But let's bear in mind that some of them have some prefixes. Okay. So the kilo here means that I have 1/100 times 10 raised to the power 3. The milli means that I have 1/50 times 10 raised to the power -3. So let's kindly take note of these. So that ends up giving us G for the C being equal to 20S. Now, what we have here is for us to calculate for resistance when given voltage and current. So we've been given two current values of which we have 1 milli and 1 micro, and we have to find the resistance having a voltage of 120 volts across the circuit. So as we know, we have resistance being equal to R is equal to V divided by I. Our V is 120 divided by our I. In the first case, we have 50 times 10 raised to the power -3. That ends up giving us 2.4 kilo ohm. And the second case, we have 120 divided by 200 times 10 raised to the power -6. And that ends up giving us 600 kilo ohms. Or someone can furthermore move the decimal point here in order to get it in the mega ohms. Resistance. All materials have their resistances. And the resistance of every material, whether an insulator, semiconductor device, or when being looked at as a conductor, the total resistance of that material depends on 4 key parameters or factors. First parameter being the type of material that it is, there. The next being the length of the material. Third being the cross-sectional area of the material. If you combine these two, the dimensions of the material. Then finally, the temperature of the material, or the temperature at which you have the material. So usually, resistivity is something that helps account for the type of material that it is. Okay, every material is having its own resistivity. And in such a case, we present it by the rule RHO, the rule sign. And the unit for resistivity is ohmmeters. As a statement here, it says that a material can be characterized by its resistivity, noted by rho, which is independent of the size and the shape. So that's just as I said, The length and the area is taking care of the dimensions, which is the size and the shape of the material. Okay, so we have a calculation here. What we have here is to compute for the resistance of a material, and that material is a copper cable. By the length of a copper cable has been given us 1,200 meters, where is our L, and we've also been given the diameter as 12 millimeters. Then the resistivity of a copper has as well been given in ohm meters. So what we need is, we know that for us to find resistance, the formula for calculating the resistance in terms of resistivity, length divided by your area, as I have used the red ink to surround it. So the formula is saying that R is equal to rho times L divided by the area. All right. So in such a case that you are looking at the conductor as such, having a diameter, and that diameter that it has been given as 12 millimeters. And the length of that copper material has as well been given as 200 meters. So in order for us to do this calculation, we need to compute for the area, and we are using pi r squared for the area, the cross-sectional area of the cable. Okay. So even as you do that, in the first stage, what is done is the 12 is used directly, which means the square affects our units as well at the end of the day. So we'll end up having this 36 pi millimeter squared. So if we need to send this into a meter case, remember this is what 10 times 10 raised to the power 3, right? So if it's 10 raised to the power 3 meters and it is squared, that means that we will end up having 10 raised to the power minus 6 meters squared. Okay, and that gives us what is here. So now we use this area as a denominator, with the length being part of our numerator and the resistivity of the copper conductor also being a part of our numerator. So at the end of the day, when we compute it, we are getting a resistance of 0.180 ohm, or someone can still compute it and say 180 milliohm. That's also correct. We have another calculation here. And for the calculation that we have here, it states that we are looking at the pure copper again. So the resistivity has been given, that is what we have here. But it's being looked at a particular temperature. Okay. And at that temperature, we are looking at the wire having a length of 1 kilometers. 1 kilometers, which is 5,000 meters. And the diameter as well has been given here. So then in the same principle, we can calculate for the area. If we calculate for the area, all we need to do is divide our numerator, which is rho L, divided by the area, which is our denominator. Then after doing that, we are having a resistance of 27.4 ohm. 27.4 ohm. Then the question went on further to say that in case we are given a current of 15 amps flowing through this very particular copper conductor, what will be the voltage across that? And we know that to find V is equal to IR. So at the end of the day, if we compute for that as well, we'll be getting 411 V, 411 volts, 411 volts. Okay, so just as I said, that there are resistivities of every material that exists. And normally, for all these materials, their resistivity, when known, gives an idea of either you categorize that material to be a conductor, a semiconductor, or an insulator, So what we have here, we see, it says resistivity varies with temperature, and some typical values of resistivity measured at room temperature are given below. We see that silver has the highest resistivity, followed by copper, then aluminum and gold. Okay, we have carbon, germanium, silicon, those three, carbon, germanium, silicon are semiconductor materials, followed by insulators, which are paper, mica, glass, Teflon. If you remember, one of the try tests or quizzes, there was a question asking for which of the following is an insulator. All right, the answer was supposed to be paper. I saw a student selecting copper. I'm very sure the student didn't read that sentence well. All right, so there's a problem here that you can try it out. It says that the resistance of a 5M length of wire is 600 ohm. Determine the resistance of an 8M of the same wire, or in the case where you are saying that, okay, now the length of the same wire when the resistance is 420 ohms. So how can we associate the effect of temperature on resistances? Temperature has quite an effect on the properties of materials. Normally, it's said that as the temperature of a material increases, most conductors will increase in resistance. However, in the case of insulators, they will decrease in resistance, whilst the resistances of some special alloys will remain almost constant at some point. So let's know the difference when the temperature is increasing. For a conductor, if you have an increase in temperature, it's a sign that there is an increase in resistance. But vice versa, in the case of an insulator, when there is an increase in temperature, that means that we are having a decrease in resistance. If the resistance of a material at 0 degrees Celsius is known, the resistance at any other temperature can be determined with the formula we have stated here. So from the formula, we have a resistance R0, okay? For a case where we are looking at temperature at 0 degrees Celsius, we have something known as temperature coefficient of resistance at 0 degrees Celsius. So that's our alpha 0. Then we can now compute for the resistance at the temperature that we are looking at. Where is the theta that we have here? Where is representing the temperature that we are looking at? In some books, you see theta being represented in terms of Kelvin. Other books, you see that it's degrees Celsius. They are the same, nothing different. So kindly take note of that. Don't be confused when you see that. All right. So there's a question for us. It says a coil of copper wire has a resistance of 100 ohms when its temperature is at 0 degrees Celsius. So that means R naught is 100 ohms. So we see that, sorry. We see R naught here as 100 ohms. Goes on to say, determine the resistance at 70 degrees Celsius, which means now theta has become 70. If the temperature coefficient of resistance of the copper at 0 degree is that value. So it's just a matter of putting your figures in the formula we had earlier on, which is this formula. Okay. Then at the end of the day, we'll be having 130.1 ohm. So that's quite practical in a way. Remember the statement I said here. When temperature increases, in the case of a conductor, what happens is we'll see a sign of an increase in what? Resistance. Copper, as we see here, is a conductor. Because it's a conductor, the temperature increased from 0 degree to 70 degree. So when we compare, at 0 degree, we have 100 ohms. But at 70 degrees, we are having 130.1 ohms. That re-emphasizes the fact as we spoke about. There's a calculation here. Here we are looking at the reverse form. Okay, so we are told to look for R naught. Say determine the resistance at 0 degrees. So we are looking at, sorry, R0. What is here? This R that has been given, we've already been given R theta. Our temperature theta has been given here as 35 degrees Celsius. And the temperature coefficient of resistance has also been given here. And that's, so at the end of the day, for this question, let me see if I can change the color. For this question, we've been given this. We've been given that. We've been given this. We've been given that. The only thing we have not been given is this. And that is what we are looking for. All right. You remember I said that conductance is the inverse of resistance. So if for a resistor, we are looking at resistivity as being rho, all right? In the case of a conductor, we are looking at conductivity. And conductivity is given as the inverse of resistivity. Its unit has been given Siemens per meter. Okay. In the same case as we looked at finding resistance based on the fact that we are given resistivity, which was rho L divided by the area A, we can find the case, we can look at the case where we are looking at conductivity as well. And for conductivity, if it's the inverse of resistivity, that means that I'll have 1 over R being equal to the area divided by rho L. All right. And that will be given, that will help me get my conductivity G. But we know that 1 over rho is our, that will help us get our conductance. our conductance. So 1 over R gives us our conductance. But we know that 1 over rho is our conductivity. So then we can say our conductivity times the area divided by the length will help us get our conductance, and that is G. So here there is a statement that we can say that, okay, that means conductance, G, is directly proportional, okay, for any given material, which is, if I select a particular material, it will be proportional, directly proportional to the area. However, it will be inversely proportional to the length, which presupposes that in the case of a resistor, resistance is directly proportional to the length for a particular material, okay, and inversely proportional to the area. So assuming I maintain the length of a specific material, assuming let's say aluminum, then keep on increasing the area, what happens is that my resistivity, okay, which is the rho, is constant for that material. So then it means that the resistance of the aluminum, when the area is increased with the length maintained, would decrease, which agrees with the fact that when I am looking at the conductance of the same aluminum, I can say that since its conductivity is constant, okay, increasing the area whilst maintaining the length to be unchanging, I will have the conductance increasing. So it will conduct more whilst I increase the area, which tells us that definitely resistance will also be what? Be reducing. Okay. What I want to talk about next is resistors in series. Then we'll move on to resistors in parallel. So for resistors in series, we say that resistors are in series when it has only one path for current between 2 points, such that the same current will be flowing through the resistors that are connected together within that topology. Okay, I don't want to use the word series here, within that topology. Therefore, what this means is that looking at point A all the way to point B, if I take resistor 1 and resistor 2, I'll see that if I have a current I flowing from point A, that current will go through R1, and the same current will flow through R2. The same for if I have current flowing from, in the case of the B, flowing from A, it will flow through R1, R2, R2, and R3. The reason being that you don't have any branch for current to divert. Okay. So the same current will flow through, in the case of a C, R1, it will flow through R2, it will flow through R3, and R4. Okay. Now, what we have next here is just the topology that has been changed, how the alignments are. That's all that has been changed. By looking at it, you see that the same current will flow through that resistor and flow through that resistor. The same will flow through this, flow through that, flow through this. If I try to drag this, if this point B, okay, if I try to drag it to align with this resistor, assuming this is R1 and R2 is here. If I try to drag it, what I'll get will be the image I have up here. In the same case, if I try to open up this to become a straight line, like a string, straight string, it will line up with that. The same for a case here. This is the same as that and is the same as that. Okay, so normally if you are able to trace a current path, you assume a current is flowing and the same current is passing through all the set of resistors without meeting any junction for a branch. Okay, then it means that it's a possible sign that you have resistors being in series. You have resistors being in series. It states here, notice that the current is the same at all points because the current has only one path. All right. So what about voltage in such a case? What about voltage? So for us to do that analysis, we have three resistors. We have R1, R2, and R3, and these are connected end to end and in series. And across these three resistors, R1, R2, and R3, we have decided to connect a voltage source here. So you remember before we got here, I taught you that if you don't know even the value of the voltage source, you can use a voltmeter to do that. So that is what we have here. The voltmeter is measuring the voltage across the cell here. All right. We have two ammeters. That's ammeter 1, that's ammeter 2. And all that they are doing is they are measuring the current flowing in the series circuit. So if we try tracing the current, you see that the current will flow in that direction through that ammeter. It will flow in that direction through that ammeter and it will return. We are using the conventional current flow. So in that case, we see that it's a series circuit, but I can find the individual voltage drops across the resistors. So I can find V1, I can find V2, I can find V3 by just connecting voltmeters across the resistors. When that is done, what can be realized is that the current measured by A1, where is the ammeters, A1 and A2, it will be the same. We have the same current reading. Okay, for the current, telling us that the circuit is a series circuit. Also, one of the things that will come up or becomes a fact is that if I take the voltage across the cell and say that that is V, if I take the individual voltages across the resistors, so V1, V2, and V3, it can be realized, or it will be realized that V will be equal to the magnitude of V will be equal to the sum of the individual voltage drops across the resistors. Therefore, we have V being equal to V1, V2, and V3. So from this same equation as we have here, we can simplify them by grouping them in terms of what? I and R. So I have this V1 can be said to be, we know the current is the same I, or we can say, okay, I'll use V1 is equal to I1, R1, V2 being equal to I2, R2, V3 being equal to I3, R3. Then also to say that, okay, then this V is equal to IT, is the total current, which is actually the same current flowing through that cell. If I know the cell's resistance, we can give it an R cell. Okay. And that will also be a V. But in case this cell resistance is not known to find this very particular V, what we can do is we can call it RT, the total resistance in the circuit. So then I can say then this V can be said as IT B times RT being equal to I1 times R1 plus I2 times R2 plus I3 times R3. But from what we've gone through with the aid of the ammeters, we know the currents are the same, which means that I1 is equal to I2 is equal to I3, and that will be equal to IT. And that we can call I. So then we can say it's equal to I. With that in mind, we'll have this equation coming up. So what we can do is if I cancel out all the i's, if these are canceled out, I'll be left with an equation as such, which says the total resistance will be equal to R1 plus R2 plus R3. So someone can say RT is equal to R1 plus R2 plus R3. It's also correct. So we have a problem here. We've been told to one, determine the battery voltage, the total resistance in the circuit. Okay. Find the value of the resistance R1, R2, and R3. If we know the voltage drops across the three resistors respectively. So in such a case, what can be done is we've been given the individual voltage drops. So for the individual voltage drops, we know of 5. And that means that this is 5 volts. If I have a voltmeter across R1, that is 2 volts. If I have a voltmeter across R2, that is 6 volts. Okay. From what we studied, this equation comes into play. It comes into play. When it comes into play, it means that to find this V, it's just a matter of having the 5 plus your 2 plus your 6. And that will give you your 13. So that means V is equal to 13 volts. Okay. So knowing this, that means what can be done next is to look at the current. We've been given the current here, and that current is 4 volts. So I can find R1 by using V1 divided by the current I. That makes it 5 divided by my current 4. In the same case, I can find R2, V2, which is equal to 2, that divided by the current, since the current is the same. then R3 as well. V3 divided by I, that gives me 6 divided by 4. Okay, and that answers this question. So it's quite easy. All right, so please try problem 3 up here. And what has been added in addition to this is that we are asked to look for the power dissipated. So that one you can use your I squared R, or you can use your V squared over your R. So we have something called the voltage divider rule. What this rule does is it helps us find the individual voltage drops in the cases where we know the total voltage across the set of resistors and the individual resistances of the resistors. So if we can look here, there's a simple trick. If you are looking for a voltage V1, make sure the resistor you have up there is actually the resistance that you have the voltage across. So I'm looking for V1. The resistance I have in my numerator is actually the resistance that I'm looking for the voltage across. So that becomes R1 divided by R1 plus R2. So your denominator is virtually just the sum with the total resistance, the sum of the resistance that you have in the circuit, with the series circuit. Okay. For V2, the same principle. What resistor are we concerned about? Since it's V2 and V2 is the one across R2, it should be R2 over R1 plus R2. And not forgetting there's the first one, I didn't say it. If you should multiply by the overall resistor, the overall voltage you have across that set of resistors. And usually this principle works when you are looking at a series circuit or you are looking at a part of a circuit, all right? It can be a branch part of a circuit that has some resistors in series that you need to find the individual voltage drops across those resistors that are in series. So we normally have to multiply by the voltage across the set of resistors that are in series. Okay, one other thing that can be done is someone can give you V1. I can give you V1 is known. I can give you R1 is known. R2 is also known. Then I'll tell you to find V. You can use this formula to do that as well. Or I can give you V1, give you V, and give you R2, then ask you to find R1. Okay, so that is a way for which you can use this formula to compute for additional parameters that are not known. All right, so the voltage divider rule is also used for what is known as the potential divider. All right. Normally, assuming I have a circuit, by the output of the circuit or the cell, the group of cell that I have, let's say it's 18 volts. So I went to buy a cell on the market. I need 12 volts at my output. Okay, to power something else that takes 12 volts. But what I had was 18 volts. So what can I do to get my 12 volts at my output? All that I can do is to carefully select some set of resistors. If I select the set of resistors rightly, then I can get my 12 volts, especially if I have, let's say, a resistance. If I know one of the resistances that I can easily get, you can assume that, okay, this one is, let's say, 3 ohms. Okay, if this is 3 ohms, then knowing my input 18 volts, my output, which is the voltage I want to use to supply another equipment, All right, I can put another equipment here or device. To supply another equipment or device, the terminals that I will use, I can use a voltage drop across a resistor, where is R2, that I will use the formula to compute for. This is known. This is 18. This also, sorry, this is 12. This is 12. My input is 18. I know R1. My R1 I know is 3. I can compute for this. Find that resistor and put it in series with my R1. Then tap with the help of some connectors, okay, to get the voltage drop across R2. And that voltage drop across R2 will be my 12 volts that I'm looking at. So this is used a lot in internal circuitries for electronics. It's also used in internal circuitry for some electrical equipment. Okay, so this a question. It's more or less playing around what I said. So it's not anything difficult. Just take your time, go through the set. You know that, you know that, you know this. If I know this, that means I can find that. Okay. Then if I can find this, I can subtract that from this to get V2. Then with the same current, I can find Rx. That's one way of doing it. Another way is just to use what I showed you, with the voltage divider rule, to compute for what you need. To compute for what you need. Now we want to look at resistors in series. So the fundamental rule that we considered for resistors in series was that the current through the set of resistors remains the same. Now, if we are looking at resistors in parallel, okay, if they are in parallel, what usually we are concerned about is that we say that the voltage that you have, if I have a voltmeter here, that's measuring the voltage here, another voltmeter here, V1, another voltmeter here, V2, I'll end up having the same voltages across each branch as I have here. But what will happen is the currents that I'll have flowing, if this is IT or the total current, at this point, it meets a node, a junction. When it meets a junction, it splits into two based on the number of branches that are connected at that junction. So I have I1, sorry, I2, this I2, and have I1 here. Okay, if I had a third, let's say there was a third branch here, we'll see that I'll have another part of the current, which I'll call I3. All right, so let's look at this sentence. This is a rule for identifying parallel circuits. Is one, if there are more than one current path between two separate points. So if I take this point, that's one point, that's also another point. I am having more than one current path. That is one current path, that's also another current path. If I'm looking at the 3 branches here, then there will be another current path here, telling me that if these current paths are all coming together at some point to give me the same current that I had splitting, okay, then I can say 1, 2, and 3, they are in parallel. between those 2 points, also appearing across each of the branches. Then there is a parallel circuit between those 2 points. So here, if we look at this, the current gets here, a portion moves in that direction. I have a current, let's say IW. IW gets here, splits, a portion gets here. Let's say IJ. IJ gets to this node, splits, a portion goes there, IV. So then I can see that all these portions of currents are also trying to sum up again to give me my IT. Then I can say, okay, R1, R2, R3, and R4 are in parallel. All right. So these are various topologies to show that we can have parallel circuits as such. This one, if you look, a current is coming this way, the a part goes there, another part goes there. The sum up moves there. Current is coming here, a part goes in that direction, another in that direction, move in that direction, side. A part moves there, a part moves there. One part moves here, another part moves there. So with this, we see that the topology of how the resistors are connected, okay, can be changed. We have it's two resistors, they are all in parallel, okay, but the topology of how it's been done in terms of the viewpoint or the arrangements makes it look a little different from the first one, but they are still the same thing. Okay, the sum of these individual currents for I1, I2, I3 would end up giving us the total currents in the circuit. And also let's know that's what I said, the V, the voltages across the set of resistors that you have in each of these branches should be the same. So if there is another resistance here, there's also another resistance here, and I'm looking at it. All right, these are sets of resistances in a branch. So if I take the total voltage here, I'll have the same total voltage there, the same total voltage there. All right, so an experiment was done with this. What the experiment shows is quite simple. It shows that we have a supply source, okay, who is a DC supply source. We go in for 4 ammeters. That's one to measure the main current coming out of the cells or group of cells. There is one A3 measuring the current moving through a resistor R3, A2 current through R2, A1 current through R1. All right. But afterwards, what was found is the currents read by A1 when added to A2 and when added to A3 gives us A. Therefore, we can say I is equal to IA1 plus I2 plus I3. So with this, the I's can be splitted using Ohm's law. Okay, the currents directly proportional to the voltage and inversely proportional to the resistance in that branch. Okay, having in mind that you are having the temperature, the thermal concept remaining constant, the temperature, provided the temperature remains constant. All right, such that this R will not be varying based on temperature. Remember, R theta is equal to R naught or RO 1 plus the coefficients times the temperature difference. So we can represent the current in these forms. Out of these, we will have this equation coming. Then, if the voltages, as we saw, are the same, when we cancel out all these voltages, we'll end up having that set of equation coming up. So if I take two, if I have only two, let's say we assume this one is not in the circuit, the third one is not in the circuit, then we'll have an equation as such with only two resistors. When simplified, we'll end up having that. If we take the inverse of it, then we'll have that coming up. Okay, so what can we say? What if they are three? What if they are three? If they are three, normally you have the product of R1, R2, R3, then a pairing of the three. So I'll have R1, R2 plus R2, R3 plus R1, R3. Okay, and that will give me my total resistance if they are three, if there are three resistors in parallel. So in line with that, there is a common rule that can be used to find the volume or the amount of current in a particular branch. Okay, and that rule says that whatever branch that I'm looking at, so whichever current it is, I should look for or find the total resistance in the circuits that I have divided by the resistors in that very particular branch times the current that was flowing before the division or before the branch was, we had a node for several branches to emerge. Okay, so there's a general rule. It applies everywhere. However, if it becomes difficult for you to use this, there is a simpler way. A simpler way is to look at two resistors at a time. And for the two resistors, if I'm looking for I1, the resistor that should be in my numerator should be the resistor in the other branch. Or if there are branches, the sum of the resistors, the total resistors in those other branches. Okay, so I have to find if there are three parallel paths, then I have to look at the total resistance of the other two parallel paths. Okay, so that means that if I'm looking for I1, for here we have only two resistors. It should be the other resistor in the other branch. Okay, so I'll have R2 divided by the sum times the current that was flowing before it met a node and split it into the various branches. So if I'm looking for I2, I'll have the other resistor in the other branch. So I2 here, the other resistor is what? R1. So R1 divided by the sum times the current that was flowing. Okay, so there's the trick. In the case of a voltage, the numerator was the resistor that we are looking at the voltage across. But in the case of a current, the numerator is the other resistors that we are not looking, the total resistance of the other branches that we are not looking for the current flowing through. So looking here, we have I1. We are concerned about R1, but we are looking at having the numerator being R2, where is the other branch that is a resistor. However, this works pretty well, and that is the application we are having here to prove that that general equation still sends us to the normal equations that we are supposed to know. Kindly try this at home It's a combination. This set is in parallel. Afterwards, they are total. I'm representing that with the hidden line. Their total resistance would be in series with R1 and R4. So assuming that is R2, 3, the total resistance of R2 and R3, it will be in series with R4. So we are told to find the PD, the voltage drop across each resistor, and also the current flowing through each of the resistors. So we know the current that will flow through R1 will still be I. The current that will flow through R4 will still be I. However, at this point, we'll have two parts for the current. The current will divide. So I'll have I2 here. I'll have I3 here, such that if I take I2 and add it to I3, it will give me my I. It will give me my I. Also taking note that if a current gets to this point, it meets a node. There are branches here. A part of the current will move in that direction, another part will move in that direction. But the volume of the current in each of the branches that we have here is dependent on the value of the resistance. So if there is I coming, I can tell that the majority of the current or most of the current will flow through the parts where you have a least resistance, whilst a small amount of the current will flow through a part where I have more resistance. So if you compute this and you have a current, let me put an asterisk by it, and then an X. You have a current such that after computing, your I2 is greater than your I3. It should straight away tell you that you have made a mistake, because it cannot be that I2 will be greater than I3, since the resistance R2 is greater than R3. But what should be happening should be such that I'll have a case where my I3 will be greater than my I2. And that means whatever I calculated will be correct. It stands a high probability of being correct if my calculations were done rightly. I should confirm that I3 will have more current flowing through it than R2. So R3 will have more current flowing through it than R2. Assuming there's something called short circuit. Assuming I do a short circuit here, it's the same circuit, but I'm adding something extra. Assuming I do a short circuit here. Okay. Which means I connect a wire from this point to that point, and the wire has an approximately negligible resistance. What usually happens is that you have a majority, if it's a negligible, let's say the resistance is 0, the wire has a resistance of 0. The current that is I flowing, when it gets here, senses a resistance here, senses a resistance in the other branch as well, and notices that, oh, there is a part that has been provided of which I don't have any resistance. So if a part has been provided of which I don't have any resistance, then the current will use that part because there is no opposition for it to flow. So in that case, if it was short-circuited, all the current I here would pass through that short-circuit part, then move through this. And what will happen is they will ignore flowing through that branch. They will ignore flowing through that branch as well. There's something for you to try at home. Kindly try this at home. Now, whenever we have a node of which the node comes into being as a result of having branches connected together at the node, a law comes into play. And that law is known as Kirchhoff's current law. So the law states that the sum of currents into a node, or total current flowing into a node, is equal to the sum of currents moving out of the load, or the total current moving out of the node. Okay, so as we see here, we have IT. IT gets to node A, splits. So we can say IT is equal to I1, I2, and I3 because it's splitted in those into those three currents. In the same way, if we look at node B, I see that I1, I2, and I3, they are all flowing into a node. And that will be equal to the sum of current moving away from the load, which is IT. Okay, so there's a definition of a node as well. A node is a point or a junction in a circuit where two or more components are connected. So we have one resistor here, another resistor, another resistor, and we have a voltage source here, and that presupposes or tells us that the voltage source is a component or an element. The resistors are elements connected together at a point or a junction. Therefore, I have a node here. There's also another node there. Another way of saying or capturing Kirchhoff's current law is to say that the algebraic sum of all the currents entering and leaving a node is equal to 0. So algebraic sum of all currents entering, which is I in, all the currents entering, plus the current moving away, which more or less, when it moves to the other side of the equal sign, becomes a minus. They will all sum up to give us a 0. So it's saying that irrespective of the currents, the number of current that are this dot, 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 dot means that I can have more currents branches coming in. All right. So the algebraic sum of all currents entering and leaving a node is equal to 0. Is equal to 0. There is another thing known as Kirchhoff's voltage law. A voltage law states that the sum of all voltage drops around a single closed path, please take note of this, in a circuit is equal to the total voltage or total source voltage in the loop. Okay, so the sum of all the voltage drops, this resistance has voltage drop V1, V2, V3, all the way to V to the nth term. Okay, the sum of them is equal to the total source voltage we have in the loop. So we have Vs is equal to V1 plus V2 plus V3 plus dot, 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 all the way to the nth term. Another way of saying it, the same Kirchhoff's voltage law, is to say that the algebraic sum of all the voltages, okay, all the voltages, we know some of the voltages as a result, they are there as sources. The other voltages are as a result of voltage drops. Okay, the sum of algebraic sum of all the voltages around a single closed path is 0. So around a single closed path is 0. So that means I can find V3 here, of which you can try doing. So you see here that you have Vs, that's Vs2. There's a voltage here, 12 volts, there's 6 volts here. So upon writing this, I can see that this is opposing the other. So I can say 50 minus 15, okay, is equal to the voltage drops. And the voltage drops that I have 12 plus 6 plus V3. So when I compute you, then you just get your V3 directly. So mathematically, you say Vs minus the voltage drops to the nth term is equal to 0. Or you can use the algebraic sum as well. The summation of all the voltages should be equal to 0. Some books will say, oh, voltage rise. They talk about the voltage source as a voltage rise. So the voltage rise will be equal to the voltage drops. Okay. So Kirchhoff's KVL, when we say KVL, Kirchhoff's voltage law, okay, says in any closed loop. So you see that it's a closed loop, it's not open. If it is open, that means there will be a break in the connection. The algebraic sum of the voltage drops, that is the product of a current and resistance, taken around the loop is equal to the resultant EMF acting in the loop. The resultant EMF acting in the loop. All right, so here we have a non-compulsory assignment. It means I'm never going to take it. It's for you to try it. The first case, we have this diagram. Okay, so for this diagram, we have resistors, and we've been told to take all resistors as 1 kilo ohm. So try and find the RT. Here as well, we have RT, but this time around this been done, let me see. It's been done with a view whereby it looks as though you are looking at a 3D image. So try and find RT as well. Each of these resistors are 1 kilo ohm. If a kilo ohm is too much for you, you can make it 1 ohm and remove the kilo and do your computations. So you have that as well. In this case, you have two views of viewing the resistor, the total resistance. So this is one view, and that is also another view. The total resistances will never be the same for any of. You can't have a case where you're having RT1 being equal to RT2 because of how the connections have been made. Okay, so if I look at this, I can see that, okay, this is in series with that. It will be in parallel with that for this, which is RT1. But from a viewpoint where I'm having RT2, I'll see that these two, they are in series, they will be in parallel with that. And they will end up also being in series with R4. Okay, there's also another one for you to try here with two different views as well. If you're able to do this, it enlarges your ability to look at circuits and easily find the total resistances as well. So here you can do the nodal movement that I told you. Move the nodes. As you move the nodes, you easily see that, oh, it's something very simple. So try this as well, and try all of them. And that brings us to the end of chapter 1. That brings us to the end of chapter 1. In chapter 2, we'll start doing the analysis. Okay. And what we will do is we will look at superposition, Thevenin's, Maxwell circulating currents, delta star transformation, which is also very needful. We'll look at the relationship that exists between Thevenin and Nortons. They are friends though. Then we will look at the maximum power transfer theorem for resistive loads. So we'll end with a try and assignment for you, which is non-compulsory. I'm never going to take it, but I'll take it in another form one day. All right. So please try these assignments for me. So at the end of the day, this is what we've done. We've gone through all the necessary captions that we had as the targets. Ohm's law, Kirchhoff's law. I've already done this ideal voltage and current sources with you already. We've looked at current divider rule, which is the division of current in parallel circuits. We've looked at the voltage division that takes place in series circuits. We've looked at resistors in series and parallel, how to compute for the total resistances in that. We've looked at conductivity. We've looked at resistivity. We've looked at conductance. Okay, so kindly try the non-compulsory that I've provided for you. God willing, we will meet in class and we'll look at some additional questions before we proceed with chapter 2. Have a great day and thank you very much. You can replay this recording whenever you have a challenge. Just replay, go back, listen to it again, and just try and follow. I believe it will be something great for you. And it's quite easier for you to understand too as well. Thank you.